Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to learn about and implement breadth-first search. Breadth-first search is a way to traverse graphs, or iterate through all of its nodes. You start with a beginning node, and you go through every level, or its closest neighbors, before going deeper into the graph. So if we start at 0, we visit 1, 2, and 3 first, before going to that next layer of nodes. So with breadth-first search, you're going wide before you go deep. This is in contrast to depth-first search, which will walk down an entire path deep into the graph before checking its next neighbor. So let's watch a video and see how breadth-first search functions. You can see we start at 0 and then visit its closest neighbors first, 1, 2, 3. Then after that, we go one level deeper and visit 4 and 6. And we continue with this logic until we reach the last node. Trees are just a special implementation of graphs, so we can use breadth-first search on a tree just as we would on a graph. You start with your root node, and then you traverse across each level before going deeper into your tree. So there are a few fundamentals required to implement breadth-first search. The primary one is that it uses a queue. So we use a queue because this allows us to get those oldest items or the first added before going deeper. So that's how we visit the neighbors before going further levels in our graph. The reason you use breadth-first search is because you want to go wide before you go deep. So you hit those closest neighbors before visiting further in the graph. You always need to track visited nodes because this prevents you from getting in cycles and making sure you visit each node only once. And finally, you use breadth-first search when you want to find the shortest path to a node. So first, let's dive a little bit deeper into why we actually use a queue. So we start with this root node, and it has 3 neighbors. So we in-queue neighbor 1, neighbor 2, and neighbor 3. Then we move forward, and we de-queue neighbor 1. So now it becomes the node we're visiting. Because it was the oldest, or the first added, it's also going to be the next one we look at. Neighbor 1 has 3 neighbors as well. We'll call it deep 1, deep 2, and deep 3. So we in-queue those. Then we de-queue neighbor 2, and it's the next node we're visiting. It has 2 additional nodes. We'll call it deeper, deeper 4, and deeper, deeper 5. So you see, because we're using the queue, we are always checking these older nodes or the first ones added, which is going to be the ones that were closest to our original node. So this is how we go level by level instead of going deep. So now let's fully walk through a breadth-first search example. Let's understand how we traverse nodes, how and why we use a queue data structure, and also why we set nodes as visited, and why we use a set data structure to track these nodes so that we only traverse through a node one time. And here we're going to start at a node called root, and there's technically not a root node in a graph. We're just calling it root here to make it very clear that it's the first node that we're visiting. So we're given this node, and we add root to the queue, and then also since we've accounted for it in the queue, we add the root to the visited node's set data structure. So we in-queue the root, and then immediately de-queue it since it's the first and only node, and then we visit it, and then add its neighbors to the queue. So we visit root, and then in-queue N1, N2, and N3. So our queue has N1, N2, and N3 in it. Since these nodes have been added to the queue and accounted for, we don't want to traverse through them again, so we also add them to the visited node's set data structure. Then, since N1 was the first added, we de-queue it first. So the first added, or the one that has been waiting in the queue the longest, is also going to be the first one that we visit. So we de-queue N1, visit N1, and then we add its neighbors to the queue. D1, D2, and D3. So in-queue D1, D2, and D3. And also notice the root is N1's neighbor, but because the root is in the visited node set data structure, we don't add it to the queue again, so this ensures we only go through it one time. Then once we're done visiting N1, we de-queue N2 because it's the next in the queue. So after visiting N1, N2 is now the oldest, or the first added, so it's the first out, or the one we visit now. So we add N2's neighbors, DD4 and DD5, and then we also add those to the visited node set data structure as well. So we added D1, D2, and D3 after we visited neighbor 1, and then we add DD4 and DD5 to the visited node set data structure as well, because they've been added to the queue. So once a node's been added to the queue, it's been accounted for, and we know that we're going to traverse through it, so we don't want to add it again. So then, after we're done visiting N2 and adding its neighbors to the queue, we then dequeue the front item again. And this time we dequeue N3, which has no neighbors other than the root, but the root's been added to the visited node set data structure, so it's not added again. So because with breadth first search, since we're using a queue, we're always using the oldest, or the one that was in the queue first, before using nodes that were added later. So we start with the root, and then added N1, N2, and N3, and then we visited N1, N2, and N3 because they were the first added. So this visited the neighbors closest to the root, before visiting the ones that were on a further level. So we visit N1, N2, and N3, and then once we're done with those, we move on to D1, which is then 2 hops away from the root. So then we dequeue D1, its neighbors are D2 and N1, which are already in the visited node set data structure, so we don't add any additional nodes, so we're done visiting D1. So then we dequeue D2, visit this node, and then we look to see if any of its neighbors can be added. They've all been visited, so then we move on to D3. We dequeue D3, all of its neighbors have been added, so we move on. We dequeue DD4, visit this node, and then check if any of its neighbors can be added. Since N2 has already been visited and it's its only neighbor, we don't add any additional nodes. And then finally, we dequeue DD5, visit this node, and check to see if we can add any more neighbors. There aren't any, so we're done. So because we use a queue and we have this FIFO, first in, first out methodology, we're always visiting the closest nodes. We start with the nodes closest to the root, N1, N2, and N3, add those to the queue, and then dequeue them, N1, N2, and N3, because the first added is the first remove, or the ones that have been waiting there the longest are the first that we look at. Then once we go through the root's closest neighbors, N1, N2, and N3, D1 is the next item in the queue. So now we're 2 levels away from the root. So we visit D1, D2, and D3, since these were the neighbors closest to N1. And then finally, we visit DD4 and 5 because these were the nodes that were closest to N2. So we work our way outward, we go wide, before going deeper into the graph. And we accomplish this by using a queue, which goes first in, first out, or visits the oldest items, or the ones that were added first, before visiting the items that were added after that. So this allows us to visit close to a node before going deeper. And this is the fundamental and core concept of a queue and why we use it with breadth first search. So with breadth first search, we find the shortest path to a node. So let's go back and understand why this is true. So let's say we start at the root and want to find the shortest path to D2. So with depth first search, you might do something like root, N1, D1, D2, which got us there in 3 hops. 1, 2, 3. So then when we visit D2, it would look like we came from D1 with depth first search. But when we use breadth first search, we visit the closest nodes first. So we go root, N1, N2, N3, and then when we get to N1, we check D1, D2, and D3. So we would see that we got to D2 from N1, and this would be in 2 hops. So 1, 2. So by visiting neighbors before going deep, this is how we find the shortest number of hops, or the fewest number of nodes to traverse through to find a given node. So this is how we get the shortest path. And so by shortest path, we just mean we get to a node by traversing through the fewest number of nodes possible, which is enabled through breadth first search because we always check the closest nodes to any given node before going deeper. So let's discuss the pros and cons of breadth first search. The pro is that it finds the shortest path. So because you're visiting neighbors before going deep, you're always going to make sure you get to any node from a source node in the fewest hops. The con is that breadth first search typically requires more memory. Because this is assumed, we use depth first search over breadth first search unless we need to find the shortest path. The reason it uses more memory is because you need to hold all those neighbors nodes, and graphs typically go wider than they do deep, so this will require more nodes to track. So before we implement breadth first search, let's just quickly walk through the logic. First, you initialize a queue and add your root node or starting node to this queue. We also need a set data structure to track which nodes we visited, so we add this first node to that set as well. Then we begin a while loop. We don't know how large our graph will be, so we just need to continue looping until we visit all the nodes. So now we dequeue that first node and we visit it, or we use it in our algorithm. Then we add this node's neighbors to our queue. Because we now have tracked these neighbors, we're going to set their status as visited by adding them to our set data structure. And we repeat this process or continue this while loop until our queue is empty, meaning we have visited all the nodes. And now we're ready to implement breadth-first search. The nodes in our graph will just be standard graph nodes. We'll have a data property, which in our case is just going to be an integer, and it will contain edges, which is going to be an array of nodes or its neighbors. When we visit a node, we're simply going to print its data. Our function is given a starting node. Then from this node, we want to traverse through all the other nodes, going wide before going deep in a breadth-first search manner. The key to implementing breadth-first search is using a queue. In our case, we're just going to use a dynamic array, which isn't going to give these constant time operations at the end, because we'll have to shift an array when we add an item to the front, but we really just want to laser focus in on the logic of breadth-first search and not get too wrapped up in the queue aspect. We also need to track the nodes we visited. And we'll do this using a set. The reason we need to track the nodes we visited is it ensures we don't go to them more than once, and will also prevent us from getting into a cycle. We initialize our breadth-first search queue with our starting node, and we'll also add this node to the set. Because we've accounted for it in our queue, we also need to say that we visited it. To iterate through a graph, we use a while loop. The reason we use a while loop is we don't know the size of our graph, so we just have to iterate until we run out of nodes. And the way we know we've run out of nodes is when our queue becomes empty. We have no more items that we've pushed to it. So while breadth-first search queue has a length greater than 0. The first thing we do is dequeue the front node. Or in this case, since we're using a dynamic array, just pop it. Then we visit this node or use it in our algorithm. In this case, we just call the visit function. Now we need to check this node's neighbors. So we go through the node's edges. And then we check if we've accounted for this child node before or not, or if we've already visited it. So if it does not have the child node in our set data structure, then we add the child to our queue. And now we're also going to mark it as visited because we've accounted for it in the queue. So visited nodes dot add child node. And this is all there is to it. You create your queue, you create the set, and then you iterate through all the nodes as long as they occur in the queue. Then, for each node, you go through its edges and add those neighbors to the queue as well. Now we have an example. We're going to build this out such that each level counts in order. So our first node is 0, then its neighbors are 1, 2, 3, and then one level deeper is 5, 6. And then on that same level is 7, 8. And finally, a level deeper, we're going to have 9. So because it's going to go across the levels, it should print out in order from 0 to 9. So now let's quickly visualize this example. The starting node is graph node with the value 0, and then we push its neighbors to its edges, 1, 2, 3. Then we see that node 1 has 5 and 6 as neighbors, node 2 has 7 and 8 as neighbors, and then node 5 has node 9 as its neighbor. We start at node 0, add it to the queue, then dequeue node 0, and then enqueue 1, 2, and 3, which are its neighbors. Then we dequeue 1, add 5 and 6 to the queue, and then we're done visiting that node. Then we dequeue number 2, we add 7 and 8 to the queue, and then we're done visiting 2. Then we dequeue 3, it doesn't have neighbors, so we're done with that level. Then we dequeue 5, we add 9 to the queue, we enqueue that, which is now the last item, and then we're done visiting 5. Then we dequeue 6, dequeue 7, dequeue 8, and dequeue 9. So by using a queue, we visit first in, first out, or use the oldest items first, so this will print them in order when they're ordered based on how close they are to the original node. So 0, 1, 2, 3 as the first level, 5, 6, 7, 8 as the second level, and then finally 9. And there it is. Now we've implemented breadth-first search. We take a starting node and we initialize a queue. We use a queue so we can add all its closest neighbors and visit those before going deep because it operates in this FIFO manner. So the closest will be the first added and also then be visited first. We continue to iterate as long as this queue has items, and we add items to the queue for every neighbor's edges. And now I hope you have a thorough understanding of how breadth-first search works, why we would use it, and feel confident and ready to use them in your coding interviews.